Hey there, you're watching the Aussie BIM Guru, and today you've reached part 7 of my feasibility series, where we're dealing with Dynamo in order to analyse the surface of a building that we've set up. So we've originally looked at just how to establish a feasibility study, going through from site controls to massing to shadow diagrams, and we've looked at a way to automate shadow diagrams in Dynamo. Now we're setting up an analysis grid on a surface, which we'll be using to analyse certain aspects of the site. Then we'll finally look at Power BI. Okay, so we're generating something a bit like this today. So basically these are adaptive components. I'll show you how to build that family very briefly. And then we're going to use Dynamo to distribute these across a surface in a spacing that we nominate. So we're inevitably going to be using these in order to basically generate a ray trace against our site and find out certain rays that clash with our site, such as buildings, because we can use this to inform certain decisions, such as analysing views. So you can see here, for example, these 3 rays that we're going to feed out from here in the direction of an object will tell us if we can actually see something from our building, so we can assess aspects of view. But as well as that, more importantly, we can generate solar analysis studies to see how many hours of sunlight these sensors will receive during a standard day. So we can use this to inform planning controls that actually require certain apartments in a building, for example, to have 2 or 3 hours of full sunlight. Yeah, there's a lot of uses for these. But we're just setting them up today, and the goal with this script, when I was developing it in the past, was to find a way to deal with lots of different types of geometry. So I experimented with a lot of different workflows because I wanted to have one script that could do all sorts of shapes. So not just flat surfaces, but curved surfaces, double curved surfaces, multitudes of shapes such as cylinders and squares, and also planes, so we could study things like plazas, for example. So it took a while to develop the best workflow, but hopefully this one will give you a good one to work with today. So we're going to use a few custom nodes in Dynamo today. One of them is the if node from the Zebra package. You can see the subversion I'm using here. And the other one is the Lunchbox package, where we're going to use the panel quadrilateral in order to generate panels across our surface. And we're going to be using Dynamo 2.0.3 today. I think you will need Dynamo 2 at least in order to build this script, at least in the way that I'm building it, because of the list management and the changes that happen between the 2 versions. So I recommend you use Dynamo 2. So without further ado, we'll get started and actually jump into a Revit model. So I've basically just got a model in the background where I've generated a mass. And I've generated a mass just by twisting a profile between 2 floors. And that's how I can generate a double curved surface that we're going to analyze as our test surface. So I'll just jump back in Dynamo. So we're going to start by just using the select face node. And I'm just going to minimize this so I can select the face in Revit temporarily. And we'll just move this over here. So the way this node works is you go select, you go to Revit, and you pick your face. And from that point we can work in Dynamo. So if I run this, and I do a fit, you'll see this is our surface that we're working with now. So we can start visualizing this element. It sometimes pays to go into settings, geometry scaling, large or extra large, depending on the size of your building, because Dynamo needs to be told roughly how big of a range it should work with. Anyway, we're going to go from there and actually get the ISO lines of this surface. So we're just going to look up ISO line, and we're going to go get ISO line. So we need to get 2. We need to get the U and the V ISO line of the surface, and I'll show you what these are in a second. So we're just going to generate a code block with 0 and 1. And essentially for our first ISO line, we need our ISO direction to be 0, and we need our parameter to be 1. And what this should generate is one of our ISO lines, which is our horizontal ISO line of our surface. And likewise then, if we generate an ISO line with ISO direction and parameter of 0, we should get our secondary ISO line from our surface. Actually no, we need to generate it based on the parameter of, I think it's 1 and 0, to get our other directions ISO line. So basically we're just telling it which side of our surface we want to analyze. And this lets us deal with a lot of complex shapes because these ISO lines curve with the surface as well. So this is a good way of us estimating how many U and V spacings we can get out of this surface. And what we're going to do is just get the length of those ISO lines. So we're going to do curve length, and we're just going to get the length of each of those. And now we know how long those lines are. And we're going to generate a code block at this point to just collect a bit of data. So the first thing we're going to get is our surface. So we're going to create a variable for surface. We're then going to get ISO line in the U and the v direction. So that's our lengths. And we're going to form a formula here. So we're just going to get the ds core function for the ceiling. So we're going to do ds core, we need to take off date time there, ds core math ceiling. And we're going to get the ceiling of the ISO u divided by the spacing, another variable that we're going to create. And you can see now we have these variables here. We're also going to get the ceiling for the ISO v divided by the spacing as well. So essentially what we need to do now is get our surface, and we'll get our ISO for u and our ISO for v. And then we need to nominate a spacing. So the spacing is essentially how spaced out you want your samples to be. So your adaptive families that we're going to place. Usually I recommend you make this a number between 1,000 and maybe 20,000, depending on the scale of the building you're working with. Usually a step of probably 500 is reasonable. That way you can just scale it up like this. And usually I set a default of maybe 5,000. And we'll just feed that into our spacing. So essentially from there we should be able to get a rough estimate of how many U and V divisions we can divide the surface into to get a roughly equal distribution of the spacing. So you can see there we've got 4 by 9, so 9 high by 4 wide. And that's what the ceiling function does essentially. What we're going to do from there is we're going to get the panel quad from the lunchbox package. And essentially the way this works is we'll feed in our surface, and then we'll feed in our U and our V from our spacings. And this will generate a set of panels and points. So I'll just run this, and you'll see that we end up with a bunch of panels, and we have the points around the edge of each panel as well. So we're going to use those panels to find out if these panels actually intersect with the surface. In this case, all of them will, but we'll need to filter a few things out to deal with very complex surfaces. One's more complex than this. So we're going to thicken our surface, both sides, and we're going to take our surface, and we'll just thicken it by about 100, I found is good. And we do want to thicken both sides as well. And this will let us deal with very abstract shaped surfaces, such as trapezoidal surfaces, where it's not necessarily a square surface that we're dealing with. It might be triangular. So if you did a panel quad against a triangular surface, you might not be able to clash all the panels against it to find the points that are relevant, because the way the quad panel works is it basically drapes across the entirety of the geometry. So if you're not fitting in a square shape, it will still try to build a square. So that's why we're doing this. Okay, so we're going to check from there if we're intersecting our points. So we're going to go geometry does intersect, and we're intersecting our thickened surface against our points in this case. And we need to count how many of these are false. So we want to find how many points are not intersecting with the surface. This is how we can find out if a panel is not fully aligned across the face of the surface. So if it's clipping a corner of a triangle, for example. So we're going to count the number of false elements, but we're going to count at level 2. So I'll just run this. So our list structure will look a little bit like this. So we're trying to find out how many of these are not clipping. At the moment, every single point is clipping the surface, which is great. So we get to keep all of these values. But from there, we're just going to set up a code block, and we're just going to find how many of these lists are greater than a threshold. So we're going to say this is our list of falses, and we want to find out basically how many are falling within a range of, we'll say from 0 to 3. So this is how you can be more tolerant of elements that aren't fully intersecting a surface. So I'll just put my threshold in there. What I might do is just pick a different surface so that you can see what I mean by this threshold. So if I just go and select the top face instead, and I run this script, it'll look a little bit different. So I'll just rotate my 3D geometry. In this case, it's actually working quite well. But you can see there, see how our UV ISO line is working in a different direction, because ISO lines always work in the orientation of Revit's north, I believe. So you can see here that we're actually getting a lot of panels that don't sit upon this face. So in order to filter those down, we're going to basically do an intersection check. So if I can just hide these panels, you'll see that the ISO lines work in a different direction to the surface. So what we're going to do is we're going to filter down based on, let's say they have to fully intersect. So what we're going to do now is we're going to do a filter by Boolean mask in order to reduce only the panels that intersect. So we're going to say of these panels back here at level 2, because in this list the panels themselves are sitting at the position of level 2. We want to mask them based on this list of masks. Okay, so we'll just put this over here because this will be an input in Dynamo Player, and we'll run this, and we'll turn off our preview for here, and we'll add a list create so we can see what's happening. And we want to take the outs, so whichever ones are not true. And we'll just go back and we'll hide our surface. And see, we only end up with the panels that fully intersect. But what we can do is we can increase our threshold. So we can say that if it has at least 3, it will be there. So you can see now we're getting more panels instead upon our surface. So that's how you can deal with, I guess, abstract shaped surfaces that are harder to analyze. But what we're going to do is just go back to our double curved surface. And that part of the workflow is very important. That one took quite a while for me to figure out, so I hope that helps you sort of take a shortcut. All right, we're just going to go back to our standard surface, and we're going to set our threshold back to 0. It has to fully intersect to be counted. Okay, so we're dealing with this surface again. And then what we can do is we can just turn off our preview. So now we're just dealing with our panels instead. Okay, so we're going to create a list, and we're going to get a point at parameter. We want to get the center of each of these panels. So we're going to take each of these surfaces, and we're going to find the point halfway along each of those panels from a U and a V perspective. So if I run this, we get the center line of each of those panels. So we'll just hide this list, and we can also go back and hide. We'll keep our base surface actually on for now, but you'll see now we have basically our sensor points where we can place our sensors. So what we need to do from there is we need to actually find out if it's pointing away from the face or into the face in a normal direction, because we need to offset these sensors just outside the building, because if we run an intersection check with rays of the sun, for example, we also want to consider the building itself. Is the building blocking the sun from this position? So we're going to push our sensors outwards away from the face of our building in order to achieve this. So we're going to get a surface normal at point, and we want to find the normal at the point of each of those upon the surface. So we're going to get our surface at level 1, and we're going to go all the way back to the start of our face back here, and then from there we need to work, I believe, at level 3 for our normals. You can see here that we're working at this level. So we're going to work with points at level 3 out of this list. And we'll run this, and we should get a normal for each of our points. So you can see for each of our 36 points, we're getting 36 normals. Okay, and then we're going to also set up a reversed vector. So we can also consider the opposite direction, because what we're going to do is we're going to set up a logic if from the zebra package, and we're going to just add a boolean, and we'll just call this normal flip. And this is an input in Dynamo Player as well. By default we won't flip the normal, but this is when you might be dealing with an internally concave face where the points need to be pushed in the opposite direction to be outside the surface. It depends on the surface's normal as well. So this just gives us the ability to flip that. And we want to be able to translate our points in this case. So we'll just take the translate geometry by vector and distance, or direction and distance. Okay, so we're going to offset our points, and we're going to offset them by a number that we can control. So we'll just get a number node, sorry, a number node. Probably not a number slider because we want the user to be specific. I find 150 is a pretty good distance in most cases. That will get you off most surfaces if you need to be off them. And we'll just call that offset. And we'll go set our inputs right at the end. Offset. Okay, and then the distance will be that vector as it results from the particular point. So if I run this, actually I must have missed something here. Geometry is coming from point. Okay, should be a vector. I might need to flatten my outputs, I believe. I'll try applying a longest to this as well. No, it still doesn't work. I'll just flatten these two lists, I believe, in order to make sure everything's working at the right level. Okay, oh, actually my distance and my direction are the wrong way around, that's why. If I run this again, great. Now we should get a set of points offset in the direction of that vector. So if I offset them by maybe, say, 3 meters, if we look over here, it's quite clear that we've created a second set of points that are offset from the original. So you'll see in our model that we're offsetting in this direction. Notice in this case that we are actually needing to flip our normal. So we'll actually flip our normal in this case in order to go away from our building surface. And there you go, we can see that now we're working in the opposite direction. But we'll just go back to 150 in this case. Okay. We can actually probably turn off this set of points so that all we're seeing is our analysis points instead. So if I rerun this, there's our analysis points. Okay. So at this point, we actually need to go and get a family that we can place at this point in order to create a sensor. So what I've got in here already is a family I built as a generic model. So I've actually used an adaptive component template to generate this family. And on the first point, I've created a sphere, essentially, and given it a radius parameter. So if you need to learn more about adaptive components, let me know and I can direct you to a tutorial I've made earlier about how to generate geometry in the adaptive environment. But essentially this family just has one type, but I've added some shared parameters to it that we can populate some data into in order to make the sensors receive some more intelligent results. So the first two I've added 2 comment fields, and note that these are shared parameters because we might need to schedule them later. So the intention of these 2 comment fields is to basically tell the sensor which side of the building it's on, and also what the building's called, because we're going to be working with design options as well, so we need to tell these sensors which option they belong to. So we might need to tell them that they're from option 1A, option 1B, that way we can filter them in schedules. I've also added 2 area fields. The intention of these is for the sensors to know the overall surface area of the face that they were derived from, and the second area is to tell you basically how much rough area each sensor is responsible for. So we have 2 count parameters as well. So the first count will be used to say how many sensors are on that face, and Dynamo will figure this out for us. And then area 2 will be the overall surface area divided by how many sensors are on that face to find out the sample size of that sensor. The second count is just locked into 1 so that we can do a count of the sensors in our schedule when we schedule our sensors later on in our sun study. So essentially that's the family. I'm happy to email that family to people if they need it as well, just in case it's too hard for someone to create. But the important part is it's an adaptive component that can be placed by point, because we're going to place them at the points from the surface. Okay, so we're going to generate some adaptive components by point. So we'll just find, this is a lunchbox node as well, I think. No, we don't want that one. I'll just search for it in my browser. I believe it's an out-of-the-box node. Yes, it's an out-of-the-box node. Great, so we will take our points, which in this case is our translated geometry. We're going to flatten at this point, just to make a flat list of points. And we're going to create a family, which is our adaptive component family. So we need to search for family types. And we'll pick our family, which in this case I've called detector. It's important that you, by default, set it to the likely name for the family. And then after that, we need to basically do some number crunching to find out what each of those parameters should be. So first we're going to get the surface area. of the initial surface that we're dealing with. So we're going to have to go all the way back to our surface. So we'll just stretch this all the way back to the start, to our initial surface. And this is going to give us something in square millimeters. I'm actually just going to freeze my adaptive component creation first, just so that when we run this, it doesn't collect that data. But essentially at this point, it should tell me the surface area in square millimeters. If you're in America, it will be a different unit again. So what we need to do is actually convert our units. So we'll use the convert between units node, and we'll feed in some area, and we'll convert square millimeters to square meters. And essentially this will give us the square meterage of our surface. Okay, so that's one parameter that we've located. And now we need to find out a few more things. So we need to know how many sensors we have. So we can just say count the number of components that were made, or count the number of points that we used to place them. And we're going to build a list at this point. So we're going to build a list with 4 items. Our first one is how many sensors we have. Our second item is the area of the face. And then we need two string inputs, which will make Dynamo player inputs. And we're going to call these our mass name and our face name. And we'll set some default values just to be mass name and face name. But essentially this is where the user can say what face of their mass they are dealing with. So we'll connect those into item 2 and item 3. And from there we'll flatten this list in order to generate a set of values that we can push into the parameters of these sensor families that we're going to place. So there you go, you can see that they're the parameters we're going to push in. We could round that area if we wanted to, but we'll let Rabbit round for us. Okay, so at this point we need to build a list of parameter names. So I'll just use a code block. Okay, so in my case, my first parameter is my count. I suggest that you set up parameters that work on your side. I'll put a square bracket at the start, just so I'm building a list as well. And then I'll keep adding parameters. So the next one is the area. The next one is the comment. Comment 1. And then the next one is comment 2. And this is where this data will be stored in the sensors. So that's why you need to add the shared parameters. Okay, so we'll just close off our list. I think in this case I've missed a close bracket as well, by the looks of it. Where have I missed my bracket? Oh, I need to do commas after each of these, not semicolons. Cool, and that gives us a list of parameters. So we're going to feed this into a set parameter by name. And we're actually going to use a list map to apply this to every single sensor. So we're actually going to feed this into list map at the end. And to each of these families, we'll apply these parameters. So we're going to feed that as our list, and that is our function. And the way that list map will work here is it will insert each component into this point of the formula and push these parameter values into these parameters at the end of the script. So we're going to unfreeze our adaptive component by point node. But what we might do is set the script up for Dynamo player, but I'll run it once out of Revit as well with Dynamo. So if we just watch how this works, essentially I'm going to rerun the script and I'll just run it, and it should place, see how it places a sensor at each of those points. And because we've offset them as well, they sit just outside the surface. So when we do with the center point line from these, they won't clash with the building if they're moving this way. However, if we go back, they will clash with the building. So that's how we can deal with self-intersecting geometry. Okay, so what I'll do is I'll just delete all of these. But before I do, I'll show you that also you can see the mass name and the face name has been populated. And also the area has been added too, and also the count of sensors. And then you can see the automatic calculation of the area sample size per sensor. So each sensor here is dealing with about 20 square meters of the surface. So that's how you can judge how much bias each sensor has if you're comparing multiple faces. Because obviously the sensors are always going to be responsible for slightly different area sizes on different faces, because no face is probably the same size as another. If you really wanted to, you could also set up UV spacing rules in both directions. So we could add like a V spacing as well as a U spacing if you want to distribute your sensors in different aspects. For now, I'm just going to stick with a uniform square grid in this case. So we'll delete these sensors and we'll run this out of Dynamo player. So we need to identify our inputs. So our first input is our face. So we'll set that by right-clicking and going is input. The next one is our spacing. So I'll just call that spacing UV. And then I'll make that an input as well. Our next inputs from there will be our threshold for points. So we'll call that our points threshold. And that lets us deal with flat surfaces a bit more easily. So we can change that to 1 or even 2 for flat surfaces to generate more points. And then we can cull them manually if there are ones that we want to keep and others we don't. Okay, the next thing we'll do is say whether we want to flip our normal direction and then how far off the surface we want to offset our points. I think from there, the only one left is what is our family that we're placing. But otherwise, I think that's all. That's all our inputs. Okay, so we're just going to save this and go out into Dynamo Player instead and just run it out of the Dynamo Player interface. So we'll just open our inputs in Dynamo Player. You can see that sometimes you get some geometry left behind from Dynamo, but it won't use it when I run Dynamo Player. It should refresh the geometry display. That's just the behavior of how Revit shows Dynamo graphically when you're working straight out of Dynamo. Okay, sometimes Dynamo Player takes a while to open the first script that you run. So let's do this face. So I'll select my face. I'll set my spacing to, I'll leave it at 5 meters and I'll set my point threshold to 0. And we will flip our normal in this case and see which side it places itself on, and we'll offset by 150. And again, you can pick your family out of this list. We actually forgot 2 inputs. So the 2 inputs we forgot were mass name and face name, because we want to tell this face what it's called and what mass it belongs to. So I'm just going to go back in and edit my script from this button here and just set those last 2 inputs as well. I could build something like data shapes with this, but I find it's better to keep these inputs the same as you work with different faces. Okay, so we're just going to find mass name and face name and also make them inputs as well. So we'll save that, close Dynamo and refresh our script. And see, it tells you that the file contents have changed, so it's aware that you've updated the script, so you need to refresh it to run it. And essentially when it reboots, it should add those extra inputs as well. Anytime now. Cool. Okay, so now you can see we've got extra inputs to deal with. So let's just call this my building, and we'll call this face 2. And we'll keep the same inputs. We'll pick this surface and we'll run. And Dynamo Player takes a little bit longer than Dynamo, but you can see it didn't take too long. You can see here it's offsetting from the surface. Now let's do face 3. Select, run, and you'll see that we can just keep generating samples in order to run these in the next part of the script. Do phase 4, select, run. So it's quite quick. Obviously bigger buildings it will take longer to generate these, but for this one it shouldn't take too long. And let's just make our sample size a bit different. Let's do a 3000 spacing instead. And you'll see that we'll end up with a different distribution of test points. So I was saying before with the top surface that it won't deal with it as easily because its normal is at a different direction to its ISO line. So if I ran it on just a point threshold of 0, we might not get enough points. In that case we sort of did, but if I put my threshold up to 1 for example, and I try again with this spacing, we may get slightly more points. So see how it fills out the face a little bit more, but you will get some peripheral points that are almost outside. So basically what's happening here is as long as there's at least 3 points of the panel intersecting with the test surface, it will allow it through. Sometimes going to a threshold of 2 or 3 is maybe too high. So if I run this on a threshold of 3, you'll see why it's probably not ideal. Because usually it will go too far outside the face. You'll get some points around these corners. So see there, that's probably a few too many for the sample. So that's why the threshold's important. What we'll do now is I'll just open our feasibility model back up again so we can run a study on our feasibility itself. So we'll just jump in, and I've set up a few test points already using this script. I might just delete one face just to show you how I generated the specific sides of the building. They can be a little bit hard to delete after if you can't select them too easily. So I might just isolate by category. And I might just delete the whole podium actually. Because I've basically generated one for each side of my building. Actually, it's a bit too hard to get rid of them all right now, so I'll just bulk delete a set of them, even though I'm deleting other samples that we don't want to delete. Or maybe I'll just delete the whole set. I'll just delete all of them. Whoop, it's getting a bit slow. Obviously, this is a lot of sensors, so expect it to be a little bit slow because it's showing you a lot graphically. Okay, but now we'll just jump back into Dynamo Player and we'll set up some of those sensors. So the good thing about having UV spacing is I know that my commercial floor is 4 meters from floor to floor. So if I go into my inputs, we'll try and get our spacings to match that vertically so that we can sort of test on a level by level basis. You can obviously manually place these points as well. You don't need to use Dynamo. And we can obviously delete them too to reduce the number of samples if you know there's a zone that the script has put them in that you don't need to test. But it's important to keep things as uniform as possible. That way you're not giving too much bias to any face. So you don't want, twice the number of sensors here as on this face, because obviously you're being doubly biased towards this area. So you might not get accurate results. So I'll just say in this case that we'll try a spacing of 4.2 meters. I find if you go a little bit above the floor to floor you're targeting, the ceiling will force it to be roughly the spacing you need. We'll set a point threshold of 0. We won't flip our normal. We'll just offset by 150. In this case, we're just going to get our family as detector, and we'll just call our mask name option 1A, and our face can be called South Podium. And for face, you basically just pick a face off your mass. So notice that as you break the mass into pieces, the faces are also breaking up as well. So you may need to join your mass if you want to analyze an entire face, or you may need to set sensors up in a few steps. Okay, but if I run this script, hopefully we should get a distribution that's roughly aligned with the floor to floor. And there you go, you can see that we've lined ourselves up on each floor perfectly. Likewise, if we're going for the tower, so if I go South Tower instead of South Podium for my face name, we can use a spacing of roughly 3200 to target our floor to floor of 3.1. I believe that should roughly line up with our floor to floor as well. So it's important to note that I'm changing my face name as I go so that my sensors get told which face they belong to for later. And that will be quite important when we schedule our results, because we're going to schedule the results these sensors give us. Cool, and you'll see there we go, it lines up roughly with the floor to floor. And you'll see obviously that each sensor has its data and also tells you its sample area. So you'll see that these ones are dealing with a sample of 9.3 meters. These ones will be dealing with a little bit more area. They'll be dealing with 15.7, so it's almost double the area that these ones are dealing with. So you may need to scale the results you get if you want to compare your commercial to your residential zone without any bias, for example. But because we know these figures for each sensor, we can use some formulas in order to manage out that bias by using just a rule of averages, basically. So that's how you can set up, I guess, surfaces for testing in Dynamo. So as I said before, we're going to use these in order to do things like view analysis and sun analysis. So in the next part, we'll be looking at view analysis using these points. So basically generating rays from a point to these points and finding out if it intersects any geometry. And then a more complicated one, which is where we're going to collect the number of sun hours in a day that these sensors can receive, which is a little bit more tricky, but far more valuable. So hopefully I'll see you in the next video. If you're not already following and subscribing, feel free to do so. Hopefully you enjoyed this video today and it gave you a really powerful tool that you can use and build on your side as well. If you have any comments or feedback, feel free to leave it down below, or you can always contact me on my email in my banner as well. Thanks for watching today. Take care. Bye.